Welcome to this gentle exploration of gravitational forces, where we'll journey together through our solar system and discover what it would feel like to stand on each of the planets that dance around our sun. Hey there, how's your day been? Wherever you are on this spinning rock we call Earth, I'm glad you've landed here. In this video, we're about to drift across our solar system, exploring the invisible force that holds us down and lifts us up. Gravity. But more specifically, the G-forces you'd feel if you stood on every planet, from the scorching plains of Mercury to the icy clouds of Neptune. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination do the floating. I would love and encourage you to watch the video till the end to learn many new things, but there is absolutely no problem if you doze off midway through the video. Before we begin this cosmic voyage, I'd love to know where you're listening from tonight. Drop a comment below. Are you nestled comfortably in your bed, perhaps with the soft glow of evening light filtering through your window? Or maybe you're taking a quiet moment during your day to pause and wonder about the forces that govern our universe. Wherever you are, know that you're part of a global community of curious minds, all drawn to the mysteries of space and the invisible forces that shape our cosmic neighborhood. If you find yourself captivated by these gentle explorations of planetary science, I encourage you to subscribe to this channel and leave a like on this video. It helps the algorithm find more sleepy minds and souls like us, who have an amazing curiosity and love for science in their minds. Here we embark on soothing journeys through the wonders of our solar system, weaving together physics and astronomy in narratives designed to both educate and comfort. Tonight, as we prepare to visit each world in our solar system, we'll discover something remarkable about the force that keeps our feet planted firmly on the ground. Let's begin. Gravity, that invisible sculptor we've come to know so well, doesn't affect us the same way everywhere in our solar system. On some worlds, you would feel crushingly heavy, your body pressed down by forces that would make even the simplest movement exhausting. On others, you might feel so light that a gentle push could send you soaring through alien skies like a feather on a cosmic breeze. This variation in gravitational pull, measured in what we call G-force, tells us profound stories about the nature of each world we'll visit. G-force is simply a way of comparing gravitational strength to what we experience here on Earth. When we say Earth has a G-force of 1, we're creating a baseline, a reference point for understanding how gravity would feel on other worlds. If a planet has a G-force of 2, you would weigh twice as much there as you do here. If it has a G-force of half, you would weigh half as much, feeling wonderfully light and buoyant. But G-force isn't just about weight. It's about the fundamental relationship between mass and distance, the cosmic dance between how much matter a planet contains and how tightly packed that matter is. A planet can be enormous, yet have weak gravity if its material is spread thin, like a cosmic cotton ball. Conversely, a smaller world packed with dense material can grip you with surprising strength, like a cosmic paperweight that refuses to let go. This gravitational diversity across our solar system emerges from the unique history of each world. Some planets accumulated vast amounts of material during their formation, becoming gravitational giants that command respect from anything that ventures near. Others remained modest in size, their gentle gravitational embrace more like a tender caress than a firm handshake. Some worlds are made primarily of light materials, gases, and ices that create bulk without much gravitational authority. Others are forged from heavy elements, dense metals, and rock that pack tremendous mass into relatively small spaces. The story of how each planet developed its particular gravitational signature is intimately connected to its position in the solar system during those chaotic early days of formation. Worlds that form closer to the Sun experience different conditions than those that coalesced in the cold outer reaches. the temperature, the available materials, and the gravitational influences of neighboring bodies all played roles in determining not just the size and composition of each planet, but ultimately the strength of gravity you would feel standing on its surface. As we prepare to visit each world in our solar system, imagine yourself as a cosmic traveler, equipped with a magical suit that allows you to survive in any environment. You'll step onto surfaces of rock and ice, experience the crushing depths of gas giant atmospheres, and feel the gentle tug of tiny worlds that barely qualify as planets. Each destination will teach you something new about the relationship between matter and gravity, between size and strength, between the cosmic forces that shaped our solar system and the very personal experience of what it means to feel heavy or light. Our journey will take us from the scorching surface of Mercury, where the sun looms enormous in the sky, to the frigid edges of the solar system, where Pluto drifts in eternal twilight. We'll experience the bone-crushing gravity of massive Jupiter and the surprisingly gentle pull of Mars, where you could leap with the grace of a ballet dancer. Each world has its own gravitational personality, its own way of embracing visitors, its own story written in the language of mass and acceleration. The gravitational forces we'll encounter tell us stories about planetary formation, about the materials that built each world, and about the cosmic processes that continue to shape our solar system today. They reveal the hidden architecture of matter itself, the way atoms and molecules respond to the fundamental forces of nature. When you feel heavy on one world and light on another, you're experiencing firsthand the universe's most basic principles of physics, feeling in your bones the same forces that govern the motion of stars and the formation of galaxies. But perhaps most wonderfully, this exploration of gravitational forces connects us to the broader story of our cosmic home. The gravity that holds you to Earth's surface is the same force that keeps our planet in its stable orbit around the Sun, that guides the Moon in its monthly dance around Earth, and that will eventually determine the fate of our entire solar system. By understanding how gravity varies from world to world, we gain insight into the fundamental forces that created the cosmic environment where life could emerge and flourish. So settle in comfortably as we prepare to embark on this gravitational grand tour. Let your breathing slow and your mind wander as we visit each planet in turn, feeling the unique gravitational embrace of worlds both familiar and strange. In the gentle rhythm of our cosmic journey, you'll discover that the force we take for granted here on Earth is actually part of a vast symphony of gravitational relationships that extends from the smallest asteroid to the most massive planet, from the birth of our solar system to its ultimate destiny among the stars. The gravitational forces that await us on each world are like fingerprints, unique signatures that tell the story of how each planet formed, evolved, and found its place in the cosmic dance. Tonight, as we begin this journey together, we'll discover that gravity is not just a force that pulls us down, but a cosmic storyteller that reveals the hidden histories of worlds both near and far. A gentle guide that connects us to the deepest mysteries of our solar system and our place within its gravitational embrace. Now that we've explored the fundamental nature of gravity and how it varies across different worlds, let's embark on a journey to understand what you would actually feel standing on each planet in our solar system. Your weight, that familiar sensation of being pulled toward the ground, would transform dramatically as you travel from world to world, creating experiences that range from the barely perceptible to the absolutely crushing. Starting with Mercury, our solar system's innermost world, you'd discover that despite being the smallest planet, it still packs a gravitational punch that might surprise you. Standing on Mercury's sun-scorched surface, you'd experience about 38% of Earth's gravity, which means if you weigh 150 pounds on Earth, you'd feel like you weigh only 57 pounds on Mercury. This reduced gravity would fundamentally change how you move and interact with your environment. Your steps would feel lighter, almost bouncy, and you could jump nearly 3 times higher than on Earth. The reduced gravitational pull would make every movement feel effortless, as if you were walking through water but without the resistance. This lighter feeling comes from Mercury's unique characteristics. Despite being composed primarily of iron and rock, making it quite dense, Mercury's small size means there's simply less mass pulling you downward. The planet's radius is only about 38% that of Earth's, and while its density is impressive at about 5.4 grams per cubic centimeter, the overall mass is just 5.5% of Earth's mass. This creates a fascinating gravitational environment where you'd feel significantly lighter while still maintaining enough grip on the surface to walk normally. Moving outward to Venus, often called Earth's twin, you'd encounter a gravitational experience remarkably similar to home. Venus pulls you down with about 90% of Earth's gravity, which means that same 150-pound person would feel like they weigh 135 pounds. This similarity isn't coincidental. Venus and Earth are nearly identical in size, with Venus having a radius about 95% that of Earth's. The planet's mass is about 82% of Earth's, creating a gravitational field that would feel familiar and comfortable to any Earthbound visitor. On Venus, your movements would feel almost natural, with just a slight reduction in weight that might actually feel pleasant. You could jump perhaps 10% higher than on Earth, and your overall sense of balance and coordination would remain largely unchanged. This gravitational similarity is one of the reasons scientists have long been fascinated by Venus as a potential target for human exploration, despite the planet's hellish surface conditions, with temperatures hot enough to melt lead and atmospheric pressure equivalent to being nearly a kilometer underwater on Earth. But it's when we arrive at Mars that things become truly interesting from a gravitational perspective. The red planet offers an experience that's dramatically different from Earth, with gravity at just 38% of our homeworld's strength. This means our 150-pound traveler would feel like they weigh only 57 pounds on Mars, the same as on Mercury, but for entirely different reasons. Mars achieves this gravitational strength through a different combination of size and density. While larger than Mercury, Mars is much less dense, composed primarily of rock and iron, but with a lower overall density of about 3.9 grams per cubic centimeter. The Martian gravitational environment would create a surreal experience for human visitors. You could jump about 2.6 times higher than on Earth, and your movements would take on an almost dreamlike quality. Walking would feel like bounding, and running would involve long, graceful strides that cover much more ground than Earth-based locomotion. This reduced gravity would have profound implications for human physiology during extended stays, potentially affecting bone density, muscle mass, and cardiovascular health over time. The reduced gravitational pull on Mars also explains many of the planet's unique features. The lower gravity allows the atmosphere to extend higher into space, contributes to the planet's ability to support massive geological features like Olympus Mons, the largest volcano in the solar system, and influences everything from dust storm dynamics to the behavior of water when it occasionally appears in liquid form. As we venture into the outer solar system, we encounter Jupiter, the gravitational giant that dominates our solar system's architecture. Standing on Jupiter's surface, if such a thing were possible given its gaseous nature, you would experience a crushing 2.36 times Earth's gravity. This means our 150-pound person would suddenly weigh 354 pounds, creating an almost unbearable sensation of heaviness that would make even the simplest movements extraordinarily difficult. Jupiter's immense gravitational pull comes from its staggering mass, more than twice that of all other planets combined. With a mass 318 times greater than Earth's, Jupiter creates a gravitational field so powerful that it influences objects throughout the solar system. The planet's density is relatively low, at about 1.3 grams per cubic centimeter, less than water, but its sheer size more than compensates for this lower density. Jupiter's radius is about 11 times that of Earth, creating a gravitational field that extends far into space and shapes the orbits of countless asteroids, comets, and even other planets. The experience of Jupiter's gravity would be overwhelming for human physiology. Your bones would feel the stress of supporting more than twice your normal weight. Your muscles would strain with every movement, and even breathing would become laborious as your chest works against the increased gravitational pull. This crushing environment helps explain why Jupiter has been able to capture and retain such a massive atmosphere, including its famous Great Red Spot, a storm larger than Earth that has been raging for centuries. Saturn presents a fascinating gravitational paradox. Despite being the second largest planet in our solar system, Saturn's gravity is only about 91% of Earth's strength. This surprising result comes from Saturn's extremely low density, just 0.69 grams per cubic centimeter, which is actually less dense than water. If you could find an ocean large enough, Saturn would float. This low density is due to Saturn's composition, primarily hydrogen and helium in various states, creating a world that's essentially a giant ball of gas and liquid. On Saturn, our 150-pound traveller would weigh about 137 pounds, feeling almost exactly like they do on Earth, but with just a hint of lightness. This near-Earth gravity comes from the delicate balance between Saturn's enormous size, with a radius about 9.4 times that of Earth, and its incredibly low density. The planet's mass is about 95 times that of Earth, but spread across such a vast volume that the surface gravity feels familiar and comfortable. The gravitational experience on Saturn would be remarkably Earth-like, allowing for normal human movement and activity. You could jump slightly higher than on Earth, and your overall sense of balance and coordination would remain largely unchanged. This similarity in gravitational pull, combined with Saturn's magnificent ring system, makes it one of the most visually spectacular yet potentially comfortable worlds in our solar system from a gravitational perspective. Uranus, the sideways planet that rotates on its side, offers yet another unique gravitational experience. With gravity at about 89% of Earth's strength, standing on Uranus would feel similar to Saturn, with our 150-pound person weighing approximately 134 pounds. This gravitational strength results from Uranus's unique composition and structure. The planet has a mass about 14.5 times that of Earth, but is spread across a radius about 4 times larger, creating a gravitational field that feels almost Earth-like. Uranus is composed primarily of water, methane, and ammonia ices, along with rock and gas, giving it a density of about 1.3 grams per cubic centimeter. This composition creates a world that's neither a gas giant like Jupiter and Saturn, nor a rocky planet like Earth and Mars, but something in between, often called an ice giant. The gravitational environment on Uranus would feel comfortable and familiar to humans, with just a slight reduction in weight that might actually feel pleasant during extended activities. Finally, we reach Neptune, the windiest and most distant planet in our solar system. Neptune's gravity is about 114% of Earth's strength, meaning our 150-pound traveller would weigh approximately 171 pounds. This increased gravitational pull comes from Neptune's composition and structure, which is similar to Uranus, but with a slightly higher density of about 1.6 grams per cubic centimeter. Neptune's gravitational environment would feel noticeably heavier than Earth, though not uncomfortably so. The additional weight would be apparent in all activities, making jumping more difficult and adding a sense of substance to every movement. This increased gravity contributes to Neptune's ability to maintain its dynamic atmosphere, including winds that reach speeds of up to 1,000 miles per hour, the fastest in the solar system. The variation in gravitational strength across our solar system tells a fascinating story about planetary formation, composition, and evolution. From Mercury's light bounce to Jupiter's crushing embrace, each world offers a unique gravitational signature that reflects its history and structure. These differences in gravitational pull have shaped not only the physical characteristics of each planet, but also their ability to retain atmospheres, support geological activity, and potentially harbor life. Understanding these gravitational variations helps us appreciate the delicate balance that makes Earth such a special place in our solar system. Our planet's gravity is strong enough to hold onto our atmosphere and oceans, while remaining gentle enough to allow the complex biological processes that have led to the development of life. As we continue to explore our solar system and search for life beyond Earth, these gravitational considerations will play a crucial role in determining which worlds might be suitable for human exploration and potential settlement. The story of gravity across our solar system is ultimately a story of diversity and wonder, revealing how the same fundamental force can create such dramatically different experiences depending on the mass, size, and composition of the worlds we encounter. Each planet offers its own gravitational personality, from the light-footed dance you perform on Mars to the heavy, deliberate movements you'd need on Jupiter, creating a cosmic ballet where gravity sets the rhythm and each world contributes its own unique steps to the performance. Now that we've traced gravity's gentle guidance from the birth of planets to the vast cosmic web, let's explore how this fundamental force shapes something far more personal and immediate: your own experience of weight and motion here on Earth and throughout our solar system. Standing on Earth, you feel gravity's pull as a comfortable, constant companion. That gentle, downward pressure you experience, the weight that keeps your feet planted firmly on the ground, represents what we call one Earth gravity, or 1G. It's the baseline against which we measure the gravitational experience on every other world in our cosmic neighborhood. But here's where our journey becomes truly fascinating. If you could somehow transport yourself to other worlds in our solar system, you'd discover that gravity isn't the same everywhere. Each planet, each moon, each celestial body has its own unique gravitational signature, its own way of embracing visitors from afar. Let's begin our tour with Mercury, the smallest planet and our Sun's closest companion. Step onto Mercury's ancient cratered surface, and you'd immediately notice something remarkable. You feel lighter, much lighter. Mercury's gravity is only 38% of Earth's, meaning that if you weigh 100 pounds on Earth, you'd weigh just 38 pounds on Mercury. Walking would become an almost bouncing experience, each step carrying you farther than you'd expect. The simple act of jumping would launch you nearly 3 times higher than on Earth. This reduced gravity stems from Mercury's modest size and density, though it's incredibly dense for its size, containing a massive iron core that makes up about 3/4 of its radius. Mercury is still much smaller than Earth. The planet's radius is only about 38% of Earth's, and its mass is just over 5% of our home planet's. These numbers translate directly into that lighter gravitational embrace. Moving outward to Venus, our solar system's hottest planet, you'd find gravity that feels remarkably familiar. Venus pulls on you with about 90% of Earth's gravitational force. The difference is subtle enough that you might not immediately notice it. Your 100-pound Earth weight would become 90 pounds on Venus. The similarity isn't coincidental. Venus and Earth are nearly twins in size and mass, with Venus having about 81% of Earth's mass packed into a sphere, only slightly smaller than our own planet. But it's when we venture to Mars that the gravitational differences become truly pronounced. The red planet, with its rusty surface and thin atmosphere, would make you feel substantially lighter. Mars' gravity is just 38% of Earth's, coincidentally the same as Mercury, though for different reasons. Your 100-pound Earth weight would drop to 38 pounds on Mars. This reduced gravity would transform your movements into something almost dance-like, with each step carrying you farther and each jump launching you higher into the thin Martian air. Mars achieves this lighter gravity through its smaller size and lower density. With about 53% of Earth's radius and only 11% of Earth's mass, Mars simply doesn't have the gravitational pull to hold you down with the same force you're accustomed to on Earth. This reduced gravity has profound implications for future Mars explorers, who will need to adapt their movements and perhaps even their equipment to account for the planet's gentler pull. The gravitational story becomes even more dramatic when we venture to the outer solar system and encounter the gas giants. Jupiter, the solar system's heavyweight champion, would crush you with its immense gravitational field. If you could somehow stand on Jupiter's surface, though no solid surface exists, you'd experience 2.5 times Earth's gravity. Your 100-pound Earth weight would balloon to 250 pounds. Every movement would become a struggle against this tremendous force. Walking would be exhausting, jumping would be nearly impossible, and the simple act of lifting your arms would require considerable effort. Jupiter's crushing gravity stems from its enormous mass, more than twice the mass of all other planets combined. Though Jupiter is much less dense than the rocky planets, its sheer size creates a gravitational field that dominates the outer solar system. This powerful pull is why Jupiter has captured so many moons, currently boasting at least 79 natural satellites in its gravitational embrace. Saturn, the ringed giant, presents a fascinating gravitational paradox. Despite being the second largest planet in our solar system, Saturn's gravity is surprisingly gentle, only about 7% stronger than Earth's. Your 100-pound Earth weight would become 107 pounds on Saturn. This relatively modest gravitational pull results from Saturn's extremely low density. The planet is composed primarily of hydrogen and helium, making it less dense than water. If you could find an ocean large enough, Saturn would actually float. Uranus and Neptune, the ice giants of the outer solar system, each provide their own unique gravitational experiences. Uranus, tilted on its side and rolling through space like a cosmic marble, would make you feel slightly lighter than on Earth. With gravity at about 89% of Earth's, your 100-pound weight would drop to 89 pounds. Neptune, the windiest planet in our solar system, pulls slightly stronger than Earth, creating a gravitational field about 14% more powerful than our home planets. Your Earth weight would increase to 114 pounds on Neptune. These gravitational variations aren't mere curiosities. They tell us fundamental stories about how planets form and evolve. The strength of a world's gravity depends on two key factors: its mass and its radius. More massive planets pull harder, but larger planets spread that pull over a greater distance, weakening it. The dance between these two factors creates the diverse gravitational landscape we observe throughout our solar system. The effects of different gravitational strengths extend far beyond how much you would weigh on each world. Gravity shapes atmospheres, influences weather patterns, and determines whether a planet can hold onto its water and air. The stronger a planet's gravity, the thicker atmosphere it can maintain. This is why massive Venus has a crushingly thick atmosphere, while tiny Mercury has virtually none. Gravity also influences the very structure of planetary bodies. On high-gravity worlds, mountains can't grow as tall because the planet's pull works constantly to level them. On low-gravity worlds, geological features can reach spectacular heights. Mars, with its reduced gravity, hosts Olympus Mons, a volcano nearly 3 times taller than Mount Everest. Such a massive structure could never exist on Earth. Our stronger gravity would cause it to collapse under its own weight. The gravitational differences between worlds also create fascinating possibilities for human exploration. On low-gravity worlds like Mars or Mercury, astronauts could carry much heavier equipment with relative ease. Construction projects would be dramatically different, with workers able to lift and move materials that would be impossibly heavy on Earth. But these same astronauts would need to completely relearn basic movements, as their Earth-trained muscles would propel them much farther and higher than expected. The implications extend to sports and recreation as well. A basketball player who can jump 2 feet high on Earth could leap over 5 feet high on Mars or Mercury. A baseball hit on Mars would travel much farther than on Earth, not just because of reduced gravity, but also because of the planet's thinner atmosphere, providing less air resistance. But perhaps most remarkably, these gravitational differences remind us of the delicate balance that makes Earth so perfectly suited for life. Our planet's gravity is strong enough to hold a substantial atmosphere and liquid water on the surface, yet gentle enough to allow complex life forms to move and thrive. It's neither the crushing weight of Jupiter nor the whisper-like pull of Mercury, but something perfectly in between, a gravitational Goldilocks zone that has nurtured life for billions of years. As you settle into rest tonight, feel the gentle, familiar pull of Earth's gravity holding you softly against your bed. Tomorrow, when you wake and take your first steps, remember that you're experiencing a gravitational force that's uniquely suited to your existence. Not too strong, not too weak, but perfectly calibrated for the remarkable dance of life that unfolds on our small blue world, spinning through space in its eternal gravitational embrace with the sun and moon. Looking at the incredible cosmic journey we've taken together, from the birth of the first galaxies to the intricate dance of celestial bodies, we now arrive at perhaps the most profound chapter of our gravitational story. The forces that sculpted the universe also shape the very worlds beneath our feet, creating the stages upon which the drama of planetary existence unfolds. But gravity's influence extends far beyond simply holding planets in their orbits. It determines the fundamental character of each world, shaping their surfaces, governing their atmospheres, and creating the conditions that make each planet utterly unique. Tonight, as we drift deeper into this cosmic lullaby, let's explore how the same force that keeps you gently pressed against your bed also carved mountains on Mars, sculpted the rings of Saturn, and created the crushing depths of Jupiter's atmosphere. Consider for a moment the remarkable diversity of worlds in our solar system. Mercury, closest to the Sun, experiences such weak gravity that a single jump could carry you 3 times higher than on Earth. The gentle pull of this small world means that any atmosphere it once possessed has long since escaped to space, leaving behind a barren, airless landscape where temperatures swing from scorching heat to bitter cold, with no atmospheric blanket to moderate the extremes. Venus, our nearest neighbor, presents a different gravitational story entirely. With a mass similar to Earth's, Venus pulls with nearly the same strength as our homeworld. But this familiar gravity has created an alien hell. The planet's substantial gravitational field has allowed it to retain an incredibly thick atmosphere, one so dense that the surface pressure equals that found nearly a kilometer beneath Earth's oceans. This crushing blanket of carbon dioxide creates a runaway greenhouse effect, making Venus the hottest planet in our solar system, despite being farther from the Sun than Mercury. Mars tells perhaps the most poignant gravitational tale of all. With only about 38% of Earth's surface gravity, the red planet represents a world caught between extremes, strong enough to hold onto a thin atmosphere, yet too weak to maintain the thick protective blanket that once allowed liquid water to flow across its surface. The low gravity on Mars means that dust storms can loft particles high into the atmosphere, creating the planet-wide dust devils that periodically shroud the entire world in a rusty haze. But it's when we venture beyond the asteroid belt that gravity's true artistry becomes apparent. Jupiter, the king of planets, possesses a gravitational field so powerful that it has fundamentally altered the architecture of our entire solar system. With a mass greater than all other planets combined, Jupiter's gravity is nearly 2.5 times stronger than Earth's. On this giant world, the very concept of a solid surface dissolves into irrelevance. Instead, Jupiter's immense gravity compresses gases into layers of increasing density, creating a world where the atmosphere gradually becomes an ocean of liquid hydrogen, which in turn becomes a core of metallic hydrogen under pressures that dwarf anything found on Earth. Jupiter's gravitational influence extends far beyond its own atmospheric boundaries. Its 4 largest moons, discovered by Galileo himself, dance in gravitational resonance, their orbits locked in mathematical harmony by the giant planet's pull. Io, the innermost of these moons, experiences such intense gravitational flexing that its rocky interior remains molten, creating the most volcanically active world in our solar system. Europa, slightly farther out, feels Jupiter's gravitational massage more gently, just enough to keep a vast ocean of liquid water flowing beneath its icy shell. Saturn, the jewel of our solar system, showcases gravity's ability to create beauty on a cosmic scale. The planet's magnificent rings exist because Saturn's gravity is strong enough to prevent the countless ice and rock particles from coalescing into moons, yet gentle enough at its outer reaches to allow these particles to spread into gossamer-thin sheets. Each ring particle follows its own precise orbit, creating the intricate patterns and gaps that make Saturn's rings one of the most beautiful sights in the cosmos. The ice giants, Uranus and Neptune, demonstrate how gravity shapes worlds in the outer darkness of our solar system. These distant worlds, with gravitational fields about 90% as strong as Earth's, have managed to capture and retain atmospheres of hydrogen, helium, and methane, despite their great distance from the Sun. The methane in their atmospheres gives both planets their distinctive blue-green coloration, a reminder that even in the cold outer reaches of our solar system, gravity continues its patient work of world-building. But perhaps the most remarkable aspect of planetary gravity is how it creates the conditions necessary for life itself. Earth's gravitational field is neither too strong nor too weak, but perfectly calibrated to create and maintain the conditions that allow complexity to flourish. Our planet's gravity is strong enough to hold on to a substantial atmosphere, yet gentle enough to allow that atmosphere to remain dynamic and life-supporting. The gravitational dance between Earth and Moon creates the tides that may have been crucial for life's emergence from the oceans onto land. The Moon's gravity, pulling on Earth's oceans, creates tidal pools where the chemistry of life could experiment with new possibilities. The same gravitational relationship stabilizes Earth's axial tilt, preventing the chaotic climate swings that would make long-term evolution impossible. Even the gravity you feel right now as you rest is part of this cosmic story. The pull that keeps you comfortably settled is the same force that holds our atmosphere in place, that drives the circulation of our oceans, that creates weather patterns and seasons. When you feel the gentle weight of blankets settling around you, you're experiencing the same fundamental force that shaped every world in our solar system and continues to govern their behavior across the vast reaches of space. The gravitational differences between worlds also reveal something profound about the nature of existence itself. On the Moon, with its gentle pull, you could leap great distances with ease, but you would also watch helplessly as any atmosphere slowly escaped to space. On Jupiter, you would be crushed by forces beyond imagination. Yet you would also witness the most dynamic and energetic atmospheric processes in the solar system. Each world's gravity creates its own unique relationship with time and space. On Mercury, the Sun would appear to move backward in the sky due to the complex gravitational dance between the planet's orbit and rotation. On Venus, the extreme atmospheric pressure created by the planet's strong gravitational field would make time itself feel different as you struggle to move through air thick as water. These gravitational variations remind us that the cosmos is not uniform, but endlessly diverse, with each world offering its own unique perspective on the fundamental forces that govern reality. The gravity that feels so familiar and comfortable here on Earth is just one note in a vast symphony of gravitational relationships that spans our entire solar system and beyond. As we continue to explore other worlds, either through robotic emissaries or perhaps someday in person, we will experience firsthand how gravity shapes not just the physical characteristics of planets, but the very experience of existence itself. Future explorers on Mars will feel the strange lightness of reduced gravity, while those who venture to the outer moons of Jupiter and Saturn will discover worlds where gravity creates conditions so alien they challenge our understanding of what it means to be a world at all. Tonight, as you drift towards sleep, remember that you are held not just by Earth's gravity, but by the same cosmic force that shapes every world in our solar system. The gentle pull you feel is your connection to a universe where gravity creates endless variety, where the same fundamental force can craft worlds of ice and fire, gas and rock, creating the diverse family of planets that make our solar system a showcase of cosmic possibility. In your dreams, perhaps you'll visit these distant worlds, feeling the strange lightness of Mars or the crushing weight of Jupiter's clouds. But when you wake, you'll return to the perfect gravitational embrace of Earth, where the force that shapes worlds has created the ideal conditions for life, for consciousness, and for the endless human quest to understand our place in the cosmic dance. Part 5. The Planetary Waltz, when worlds dance in perfect harmony. So far, we've journeyed through the cosmic architecture of gravity, watching how this invisible force shapes everything from the smallest moons to the vast galactic superclusters. We've seen how planets find their rhythms in the solar system's grand symphony, each world settling into its own unique tempo around our sun. But now, we turn to something truly extraordinary. The moments when celestial bodies don't just orbit independently, but lock into perfect mathematical harmony with one another. Picture this. You're listening to an orchestra where each musician plays their own part, but occasionally, certain instruments synchronize into the most beautiful harmonies. This is exactly what happens in our solar system and beyond, where gravity acts as the cosmic conductor, guiding planets and moons into relationships so precise they would make a mathematician weep with joy. These gravitational harmonies are called orbital resonances, and they represent some of the most elegant examples of how chaos can spontaneously organize itself into order. When two or more celestial bodies orbit with periods that form simple mathematical ratios, like 2:1, 3:2, or 4:2.1, they create what astronomers call resonance. It's as if the universe has discovered its own internal rhythm, keeping time across millions of miles of empty space. The most famous example of this cosmic choreography lies right here in our own solar system, in the fascinating dance of Jupiter's largest moons. Io, Europa, and Ganymede have settled into what's called a 4:2.1 resonance. For every 4 orbits that Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes precisely 1. This isn't some cosmic coincidence that happened overnight. It's the result of millions of years of gravitational fine-tuning, where these 3 worlds gradually adjusted their orbits until they found this perfect mathematical relationship. But why do these resonances form at all? The answer lies in gravity's patient, persistent nature. When moons or planets first form, their orbits are often chaotic and unstable. Some might be on collision courses, others might be drifting away into the darkness of space. But gravity, that tireless sculptor we've come to know so well, slowly nudges these bodies into stable configurations. It's like a cosmic tuning fork, gradually bringing discordant notes into harmony. The process can take millions of years. Each time the orbiting bodies reach the same relative configuration, they experience a tiny gravitational tug. Individually, these tugs are insignificant, barely measurable, even with our most sensitive instruments. But when they occur repeatedly, always at the same point in the orbit, they accumulate into powerful forces that can reshape entire planetary systems. This is gravity working not through brute force, but through patience and precision. It's the difference between a sledgehammer and a master craftsman's delicate tools. Where other forces might shatter or scatter, gravity gently guides celestial bodies into configurations of exquisite mathematical beauty. The resonances we observe today are the result of countless small adjustments, each one moving the system incrementally toward greater stability and harmony. And the dance continues even now. These resonances aren't static, frozen arrangements, but living, breathing relationships that continue to evolve over cosmic time. Consider the remarkable relationship between Neptune and Pluto. These two worlds share a 3.2 resonance, with Neptune completing 3 orbits around the Sun for every 2 that Pluto manages. This relationship actually protects Pluto from ever getting too close to Neptune, despite their orbits appearing to cross when viewed from certain angles. It's like having a cosmic dance partner who ensures you never step on each other's toes, even when your paths seem to intersect. The asteroid belt between Mars and Jupiter tells another story of resonance, though this one speaks of absence rather than presence. There are gaps in the asteroid belt, called Kirkwood gaps, where very few asteroids are found. These empty spaces correspond exactly to orbital periods that would create resonances with Jupiter. Any asteroid unlucky enough to find itself in one of these resonant relationships gets its orbit gradually perturbed by Jupiter's massive gravitational influence, eventually being ejected from the belt entirely. It's as if Jupiter is a cosmic gardener, carefully weeding out asteroids that dare to dance too closely to its rhythm. But perhaps the most spectacular example of gravitational choreography lies in Saturn's ring system. Those magnificent rings, which have captivated human imagination since Galileo first glimpsed them through his telescope, are sculpted and maintained by a complex web of gravitational resonances with Saturn's many moons. The gaps in the rings, like the famous Cassini division, exist because particles in those regions would be in resonance with moons like Mimas. The repeated gravitational tugs from these moons gradually clear out the ring particles, creating the beautiful structure we observe today. What makes these resonance systems so remarkable is their stability. Computer simulations show that planets in resonance can maintain their orbital relationships for billions of years, far longer than non-resonant systems. The resonances act like gravitational safety nets, preventing the system from descending into chaos, even when subjected to external perturbations. This stability emerges from a beautiful principle. Resonance systems naturally settle into configurations that minimize the total energy of the system while maintaining angular momentum. It's as if gravity is an artist, constantly adjusting and fine-tuning until it achieves the most elegant possible arrangement. The discovery of exoplanets has revealed that orbital resonances aren't just a curiosity of our own solar system, but a fundamental organizing principle throughout the galaxy. The Kepler Space Telescope and other planet-hunting missions have shown us that resonant chains of planets are surprisingly common around other stars. Some of these systems are even more tightly packed and precisely tuned than anything we see in our own solar system. The TRAPPIST-1 system, for example, contains 7 Earth-sized planets locked in a complex chain of resonances. Moving outward from their star, the planets maintain period ratios of approximately 8:5, 5:3, 3:2, 3:2, 4:3, and 3:2. It's like a cosmic music box, with each planet keeping perfect time with its neighbors in an intricate, never-ending performance. These discoveries have profound implications for our understanding of how planetary systems form and evolve. They suggest that the migration and resonant capture of planets is not just a feature of our own solar system, but rather a fundamental process in planetary system formation throughout the universe. The study of orbital resonances has also revolutionized our understanding of planetary migration. Computer simulations show us that in the early solar system, planets didn't simply form where we find them today. Instead, they migrated inward and outward, pushed and pulled by gravitational interactions with the disk of gas and dust from which they formed. During this migration, planets could capture each other into resonances, creating chains of worlds locked in mathematical harmony. This process helps explain some of the puzzling features of our solar system. Why, for instance, do we find so many asteroids grouped together in the asteroid belt, while other regions remain relatively empty? The answer lies in resonances with Jupiter. The massive planet's gravitational influence creates a complex pattern of stable and unstable zones throughout the asteroid belt. Asteroids in resonance with Jupiter can remain stable for billions of years, while those in non-resonant orbits are gradually perturbed and removed. Even more fascinating are the resonances we've discovered in the outer reaches of our solar system. The Kuiper Belt, that distant realm of icy bodies beyond Neptune, is organized by a complex web of resonances with the giant planet. Objects like Pluto are part of a whole family of Plutinos, small worlds that share similar resonant relationships with Neptune. These resonances extend their influence far beyond the realm of planets and moons. Binary star systems often exhibit resonant relationships, with their orbital periods locked in simple ratios. Even entire galaxies can be caught in gravitational resonances, their orbits around galactic centers synchronized in ways that persist for billions of years. The mathematics underlying these resonances reveals something profound about the nature of our universe. At its heart, it's about the accumulation of small effects over vast periods of time. Each gravitational interaction, each tiny tug and pull, contributes to a larger pattern that emerges over cosmic timescales. It's a reminder that even in the apparent chaos of planetary formation, there are underlying principles of order and harmony. As we continue to discover new exoplanetary systems, we're finding that resonant configurations are surprisingly common. This suggests that the formation of stable, long-lived planetary systems naturally tends toward these harmonious arrangements. It's as if the universe has an inherent preference for elegance, constantly working to transform the random violence of planetary formation into the serene clockwork of orbital resonance. Tonight, as you drift towards sleep, remember that you're part of a cosmos where gravity conducts an endless symphony of motion. Worlds dance in mathematical harmony across the darkness, their orbits locked in relationships so precise they would make a clockmaker weep with envy. In this grand gravitational ballet, every planet knows its place. Every moon keeps perfect time, and the music of the spheres plays on, eternal and beautiful, in the vast concert hall of space. The cosmic dance continues, not just in the vastness between stars, but in the delicate clockwork of orbital mechanics that keeps our own world spinning safely through the darkness, held in the gentle embrace of gravitational harmony that has been playing since the solar system was young. Now here's where things get absolutely fascinating, and I promise this will change how you think about planetary gravity forever. We've explored how different worlds would feel under your feet. But there's something far more profound happening here, something that connects every single gravitational experience we've discussed to the very fabric of space and time itself. You see, when we talk about feeling twice as heavy on Jupiter, or floating weightlessly on smaller moons, we're not just describing numbers on a scale. We're describing the fundamental force that literally shapes reality as we know it. And the most mind-blowing part? Every single gravitational field we've explored tells a story about how that world came to be, how it evolved, and what its future holds. Think about this for a moment. When you imagine standing on Mars and feeling that lighter bounce in your step, you're not just experiencing reduced gravity. You're feeling the direct result of Mars losing its thick atmosphere billions of years ago. That weaker gravitational pull we calculated. It's the reason Mars couldn't hold on to its water, couldn't maintain its protective magnetic field, and couldn't sustain the kind of robust atmosphere that Earth enjoys today. But here's what's truly extraordinary, and this is something most people never consider. The gravitational force you'd experience on any planet is actually a window into that world's entire history. Every gram of mass that contributes to that gravitational pull has a story. The iron in a planet's core, the silicon in its rocky mantle, the frozen water in its polar caps. All of these materials were forged in the nuclear furnaces of ancient stars, scattered across space by supernovae, and then slowly, patiently, gathered together by gravity itself over millions of years. When we calculated that you'd weigh about 170 pounds on Saturn, despite its enormous size, we weren't just doing math. We were describing the end result of a cosmic process that began when our solar system was nothing more than a swirling cloud of gas and dust. Saturn's lower density, which gives it that surprisingly moderate surface gravity, tells us that this magnificent world formed in the outer reaches of our solar system, where lighter elements like hydrogen and helium could condense and accumulate. And this is where the story becomes even more captivating. The gravitational differences between planets aren't random quirks of nature. They're the signatures of entirely different evolutionary paths. Venus, with its crushing 224-pound gravitational pull, represents what Earth might have become if it had formed just a little closer to the Sun. That extra gravitational strength comes from a world that became so hot, its oceans boiled away, leaving behind a dense, CO2-rich atmosphere that creates a runaway greenhouse effect. Meanwhile, Mercury's modest 63-pound pull tells the story of a world that was literally stripped down to its core by the young sun's intense heat and solar wind. What you'd feel standing on Mercury isn't just reduced gravity. It's the gravitational signature of a planet that lost most of its outer layers early in its formation. But let's push this understanding even further, because the implications are staggering. Every planetary gravity we've discussed exists within what Einstein showed us is curved space-time. When you feel that bone-crushing 529-pound weight on Jupiter, you're not just experiencing a stronger gravitational pull, you're experiencing more severely curved space-time. The fabric of reality itself is more warped around Jupiter than around Earth. This means that time itself runs slightly differently on each world we've visited. On Jupiter, where gravity is strongest, time would tick just a tiny bit slower compared to Earth. On Mars, with its weaker gravity, time would run slightly faster. These differences are incredibly small. We're talking about fractions of nanoseconds, but they're real, measurable, and absolutely fundamental to how the universe works. Now, here's something that will completely change your perspective on planetary gravity. Every single gravitational field we've explored is actually unstable over cosmic timescales. The gravity you'd experience on any planet today is different from what it was 1 billion years ago, and it will be different again 1 billion years from now. Planets are constantly losing mass to space through atmospheric escape. gaining mass from cosmic dust and meteorite impacts, and even changing their internal structure as they cool and evolve. Mars, for instance, is slowly losing its atmosphere to space. That 79-pound weight you'd experience there today was probably closer to 85 or 90 pounds billions of years ago, when Mars had a thicker atmosphere. The planet is literally getting lighter over time as its atmospheric mass bleeds away into space. Jupiter, on the other hand, is still slowly contracting from its formation. It's actually generating more heat from this contraction than it receives from the Sun. This means that Jupiter's gravity is very, very slowly increasing over time as the planet compresses itself under its own immense weight. But here's perhaps the most profound realization of all. The gravitational experiences we've calculated for each planet represent just a single moment in cosmic time. Our entire solar system is engaged in a gravitational dance that's been choreographed over billions of years. The Moon is slowly spiraling away from Earth, which means Earth's tides are gradually weakening. Mars's small moons are spiraling inward and will eventually be torn apart by tidal forces. The entire system is dynamic, evolving, constantly changing. This brings us to something absolutely remarkable about gravitational fields. They're not just local phenomena. Every planet's gravity influences every other planet, creating a complex web of gravitational interactions that extends throughout the entire solar system. When you calculated your weight on Jupiter, you were actually calculating the result of gravitational forces that have been fine-tuned by billions of years of planetary interactions. The asteroid belt between Mars and Jupiter exists precisely because Jupiter's enormous gravitational influence prevented the formation of a planet in that region. The gaps in Saturn's rings are carved out by gravitational resonances with Saturn's moons. Even the orbits of distant objects in the outer solar system bear the gravitational fingerprints of the giant planets. And this is where our understanding of planetary gravity connects to something truly cosmic in scale. The same gravitational processes that determine your weight on different planets are the forces that built galaxies, that cause stars to form, that will ultimately determine the fate of the universe itself. Gravity is the architect of cosmic structure on every scale, from the smallest asteroid to the largest galaxy cluster. When you imagine bouncing across the surface of Earth's moon at 1/6 your normal weight, you're not just experiencing reduced gravity, you're experiencing the gravitational signature of a world that was born from one of the most violent events in our solar system's history. That lower gravity exists because the moon formed from debris blasted into space when a Mars-sized object collided with the early Earth over 4 billion years ago. The iron core that gives Earth its magnetic field and contributes to its gravitational pull. That iron was delivered by countless asteroid impacts during a period called the Late Heavy Bombardment. The water that makes up a significant portion of Earth's mass and contributes to the 1G gravity we experience. Much of it likely came from comets that formed in the outer solar system and were scattered inward by gravitational interactions with the giant planets. This means that the gravity you feel right now, sitting wherever you are, is the cumulative result of cosmic processes that span the entire history of our solar system. You're not just experiencing Earth's gravitational pull, you're experiencing the gravitational signature of billions of years of cosmic evolution. And here's something that will absolutely blow your mind. The gravitational forces we've calculated for each planet are actually creating the conditions for their own future evolution. Jupiter's massive gravity is slowly pulling in comets and asteroids, gradually increasing its mass. Mars's weaker gravity is allowing its atmosphere to escape, which reduces atmospheric pressure and allows more water to sublimate directly from ice to vapor, further reducing the planet's mass. Even more incredibly, the gravitational interactions between planets are slowly changing the architecture of our entire solar system. computer simulations show that planetary orbits are not perfectly stable over billion-year timescales. The gravitational dance between planets creates a kind of cosmic clockwork that can occasionally go chaotic, potentially ejecting planets from the solar system or causing them to spiral into the sun. This is why understanding planetary gravity isn't just about knowing how much you'd weigh on different worlds. It's about understanding the fundamental forces that shape planetary evolution, climate, and even the potential for life itself. Every gravitational field we've explored represents a unique solution to the cosmic puzzle of how matter organizes itself under the influence of gravity. The bone-crushing gravity of Jupiter creates pressures so intense that hydrogen becomes metallic. The gentle gravity of Mars allowed its early atmosphere to escape, transforming it from a potentially habitable world into the cold, dry desert we see today. The moderate gravity of Earth has created the perfect conditions for plate tectonics, which recycles carbon and maintains stable temperatures over geological time. Understanding these gravitational differences gives us crucial insights into the search for life beyond Earth. When we discover exoplanets orbiting other stars, one of the first things we calculate is their surface gravity. Too strong, and the atmosphere might become so thick that the surface is uninhabitable. Too weak, and the atmosphere might escape entirely, leaving the planet barren. The gravitational sweet spot that Earth occupies, strong enough to hold on to its atmosphere and water, but not so strong as to trap excessive gases, represents just one of many factors that make our planet uniquely suited for life as we know it. This is why every measurement of planetary gravity we've discussed contributes to our understanding of habitability throughout the universe. As we float through the cosmic immensity, suspended between the familiar pool of Earth and the vast unknown of space, we find ourselves contemplating one of the most profound questions in all of science. What would it feel like to stand on the surface of another world? The answer lies not just in the alien landscapes and exotic atmospheres we might encounter, but in something far more fundamental and immediate. The very sensation of weight itself, governed by the gravitational embrace of each celestial body. Every world in our solar system offers its own unique gravitational signature, its own particular way of holding you against its surface. These differences aren't merely academic curiosities. They represent the fundamental forces that have shaped the character of each planet, carved their landscapes, sculpted their atmospheres, and determined whether they could nurture the delicate chemistry of life itself. The gravity you experience on any world tells the story of that world's formation, its internal structure, and its place in the cosmic dance that has unfolded over billions of years. To understand these gravitational variations, we must first appreciate the elegant simplicity of the relationship that governs them. Gravity's strength depends on two factors: the mass of the world beneath your feet and your distance from its center. A more massive world pulls you down with greater force, while a larger world holds you farther from its dense core, weakening the gravitational embrace. It's this interplay between mass and size that creates the remarkable diversity of gravitational experiences across our solar system. Let's begin our journey on Mercury, the innermost planet, where the sun looms enormous in the sky, and the landscape bears the scars of billions of years of cosmic bombardment. Here, standing on the heavily cratered surface, you would experience about 38% of Earth's gravity. Each step would carry you farther than you expect. Each jump would lift you higher, and every movement would feel strangely effortless. This reduced gravity reflects Mercury's modest size and composition. It's a world where a dense iron core makes up an unusually large portion of the planet's mass, yet the overall gravitational pull remains gentle compared to our homeworld. The sensation of walking on Mercury would be dreamlike, almost ethereal. Your body, evolved for Earth's gravitational environment, would feel remarkably light. a person weighing 70 kilograms on Earth would feel as though they weighed only about 27 kilograms on Mercury's surface. This isn't merely a difference in numbers. It's a fundamental change in how your body would interact with the world around you. Your muscles, designed to work against Earth's pull, would suddenly find themselves overpowered for the task at hand. Moving to Venus, our planetary neighbor shrouded in dense clouds of sulfuric acid, the gravitational experience becomes more familiar, yet subtly different. Venus pulls you downward with about 90% of Earth's gravity, a difference so slight you might barely notice it at first. Yet this near equality isn't coincidental. Venus and Earth are often called twin planets because of their similar sizes and masses. Standing on Venus's surface, beneath those crushing clouds and in temperatures hot enough to melt lead, you would feel almost at home, gravitationally speaking. Each step would feel natural, each movement familiar, as if you were walking on a hellish version of Earth itself. The similarity in gravitational pull between Venus and Earth tells us something profound about these worlds' shared heritage. Both planets formed from the same disk of material around the young sun, accumulating similar amounts of rocky material and developing comparable internal structures. Yet despite this gravitational kinship, Venus chose a dramatically different evolutionary path, its greenhouse atmosphere creating surface conditions that would be instantly lethal to Earth life. It's a reminder that gravity, while fundamental, is just one factor in determining a world's character and habitability. Our journey continues to Mars, the red planet that has captured human imagination for centuries. Here, the gravitational experience shifts dramatically. Mars pulls you downward with only about 38% of Earth's gravity, identical to Mercury, despite being a much different world. This coincidence illustrates how the interplay between mass and size can produce similar gravitational effects through different combinations of planetary properties. Mars is larger than Mercury, but also much less dense, with a lower proportion of heavy elements in its composition. Walking on Mars would transform you into something resembling a superhero from Earth's perspective. Your stride would become a gentle bound, each step carrying you nearly 3 times farther than you're accustomed to. Jumping would become an art form. You could leap over obstacles that would seem impossible on Earth, and the sensation of falling would be slowed to a gentle, almost floating descent. This reduced gravity has profound implications for any future human settlement on Mars, affecting everything from architecture to athletics, from the way water flows to how dust settles in the thin atmosphere. The low gravity on Mars also tells the story of a world that couldn't hold on to its original atmosphere. Unlike Earth, with its strong gravitational pull that keeps our atmosphere tightly bound, Mars's weaker gravity allowed much of its early atmosphere to escape to space over geological time. This atmospheric loss, combined with the planet's greater distance from the Sun, transformed Mars from what may have been a warmer, wetter world into the cold, dry desert we observe today. The gravity you would feel on Mars is thus intimately connected to the planet's climatic history and its current inability to support liquid water stably on its surface. Venturing into the outer solar system, we encounter Jupiter, the giant among planets, where the gravitational experience becomes almost incomprehensibly intense. Jupiter's surface gravity is about 2.5 times that of Earth, but this figure is somewhat theoretical, since Jupiter has no solid surface to stand upon. If you could somehow find yourself at the level where atmospheric pressure equals that at Earth's sea level, you would be crushed by a gravitational force that would make every movement a tremendous effort. On Jupiter, a person who weighs 70 kilograms on Earth would feel as though they weighed about 175 kilograms. Simply standing upright would require enormous effort, and walking would become a slow, laborious process. Your cardiovascular system would struggle to pump blood against this increased gravitational load, and your bones and muscles would experience stresses far beyond what they evolved to handle. This intense gravity reflects Jupiter's enormous mass. It contains more material than all the other planets combined, creating a gravitational well so deep that it influences the orbits of objects throughout the solar system. Jupiter's powerful gravity has played a crucial role in shaping our solar system's architecture. It acts as a cosmic shepherd, its gravitational influence preventing the asteroid belt from forming into a planet and protecting the inner solar system from many comets and asteroids that might otherwise threaten Earth. The planet's gravity is so strong that it has captured dozens of moons, creating a miniature solar system with its own complex dynamics and fascinating worlds like Europa and Io Saturn. The ring jewel of our solar system presents a fascinating gravitational paradox. Despite being the second largest planet, Saturn's surface gravity is only about 7% stronger than Earth's, pulling you downward with roughly 1.07 times our planet's force. This surprisingly modest gravitational pull results from Saturn's remarkably low density. It's the least dense planet in our solar system, with an average density less than that of water. If you could find an ocean large enough, Saturn would actually float. The experience of standing on Saturn, were such a thing possible, would feel remarkably similar to standing on Earth. Your weight would increase by only about 7%, a difference so small you might not immediately notice it. Yet this gravitational similarity masks the profound differences between these worlds. Saturn's low density reflects its composition. It's primarily hydrogen and helium, the lightest elements in the universe, compressed into a world nearly 10 times Earth's diameter. The planet's famous rings, those magnificent sheets of ice and rock that have inspired wonder for centuries, are held in their precise orbits by this same gravity that would feel so familiar to an Earth-born visitor. Uranus and Neptune, the ice giants of the outer solar system, offer their own unique gravitational experiences. Uranus pulls you downward with about 89% of Earth's gravity, while Neptune's pull is slightly stronger at about 114%. These similar gravitational strengths reflect the planet's comparable masses and sizes, despite their great distance from each other and from the Sun. Standing on Uranus would feel like standing on a world where everything is slightly lighter, where your movements would have a subtle ease that might not be immediately apparent, but would become noticeable over time. Neptune, conversely, would feel slightly heavier than Earth, adding a modest but perceptible weight to every step. These gravitational differences tell us about the internal structure of these distant worlds. They're composed primarily of water, methane, and ammonia ices surrounding rocky cores, creating densities and gravitational fields that happen to bracket Earth's own values. The gravitational experiences on these outer planets are intimately connected to their atmospheric dynamics. The strong gravity helps these worlds retain their thick atmospheres of hydrogen, helium, and other gases, creating the dynamic weather systems we observe from afar. Neptune's slightly stronger gravity contributes to its remarkably active atmosphere, with wind speeds reaching over 2,000 kilometers per hour, the fastest in the solar system. Even tiny Pluto, no longer classified as a planet, but still a fascinating world in its own right, offers its own unique gravitational story. With only about 6% of Earth's gravity, Pluto would transform any visitor into a being capable of superhuman feats by Earth standards. A simple step would become a soaring leap, and jumping would carry you to heights that would seem impossible on Earth. This weak gravity reflects Pluto's small size and low density. It's a world composed primarily of rock and ice, with a mass only about 1/5 that of Earth's moon. The gravitational tour of our solar system reveals something profound about the nature of worlds and their formation. Each planet's gravitational signature is like a fingerprint, unique and revealing. It tells us about the conditions in the early solar system when these worlds were forming, about the materials that were available at different distances from the Sun, and about the complex processes that shaped each world's final character. The rocky inner planets, Mercury, Venus, Earth, and Mars, all formed from similar materials, but ended up with different gravitational signatures based on their sizes and how much material they managed to accumulate. The gas giants, Jupiter and Saturn, grew large enough to capture hydrogen and helium directly from the solar nebula, creating worlds of immense mass and correspondingly strong gravity. The ice giants, Uranus and Neptune, formed farther out where water and other compounds could freeze, creating worlds with intermediate gravitational characteristics. These gravitational differences have profound implications for the possibility of life on each world. Earth's gravity is strong enough to hold onto a substantial atmosphere and liquid water, but not so strong as to create crushing conditions at the surface. It's a gravitational Goldilocks zone that has allowed life to flourish for billions of years. Mars' weaker gravity contributed to its atmospheric loss and current inhospitable conditions, while Venus's Earth-like gravity wasn't enough to prevent its runaway greenhouse effect. The moons of the outer planets add another layer of complexity to our gravitational tour. Europa, one of Jupiter's moons, has only about 13% of Earth's gravity, yet this weak pull may be perfectly suited for maintaining the subsurface ocean that could harbour life. Titan, Saturn's largest moon, with about 14% of Earth's gravity, has managed to retain a thick atmosphere and liquid methane lakes on its surface, a testament to how gravitational and atmospheric conditions can create unexpected environments. As we contemplate these gravitational variations across our solar system, we're reminded that gravity is far more than just a force that keeps our feet on the ground. It's the architect of worlds, the sculptor of atmospheres, and the choreographer of the cosmic dance that has played out over billions of years. Each world's gravitational signature tells a story of formation, evolution, and the delicate balance of forces that determine whether a world can support the complex chemistry we call life. The diversity of gravitational experiences across our solar system also speaks to the remarkable adaptability that life might require to exist in different environments. While Earth's gravity feels natural to us because we evolved within it, life on other worlds would need to adapt to very different gravitational conditions. The weak gravity on Mars might favour tall, slender organisms, while the strong gravity on Jupiter's moons might favour compact, robust forms of life. Understanding these gravitational differences is crucial for humanity's future as a spacefaring species. Any human settlement on Mars would need to account for the physiological effects of reduced gravity on bone density, muscle mass, and cardiovascular health. Visitors to the outer planet's moons would need to adapt to gravitational conditions that would make every movement feel like floating through a dream. The gravitational forces we've explored also play crucial roles in shaping the geological activity of each world. Strong gravity can drive more intense tectonic activity, while weak gravity might allow for more exotic geological processes. The fascinating geology of places like Io, Jupiter's volcanically active moon, is driven in part by the tidal forces created by Jupiter's immense gravity. As we continue to explore our solar system with robotic probes and dream of eventual human missions, the gravitational characteristics of each world will play crucial roles in mission design. Landing on a high-gravity world requires more fuel and stronger equipment, while operating on a low-gravity world presents its own unique challenges in terms of traction and stability. The story of gravity across our solar system is ultimately a story of diversity within unity. While all these worlds follow the same fundamental laws of physics, The different combinations of mass, size, and composition create a remarkable variety of gravitational environments. From the gentle pull of tiny Pluto to the crushing embrace of massive Jupiter, each world offers its own unique perspective on how gravity shapes the character of celestial bodies. Part 8. The gravitational fingerprints of our cosmic neighborhood. We've journeyed through the vast cosmos together, from the birth of the first stars to the grand architecture of galactic superclusters. We've witnessed how gravity sculpts the universe on the grandest scales, weaving dark matter into cosmic webs that stretch across billions of light years. But now, as we drift closer to home in our cosmic voyage, let's explore something more intimate, yet equally profound: the unique gravitational signatures of each world in our solar system, and how these invisible forces create the conditions that make each planet a distinct character in gravity's grand performance. You see, gravity isn't just the universal force that binds galaxies together. It's also the cosmic fingerprint that gives each world its own personality, its own story written in the language of mass and acceleration. Every planet, every moon, every asteroid carries its own gravitational signature, as unique as a snowflake, yet all following the same elegant mathematical principles that govern the cosmic dance. Let's begin our tour with Mercury, the swift messenger of our solar system. This small, dense world racing around the Sun every 88 Earth days presents us with our first lesson in planetary gravity. Standing on Mercury's surface, you would experience about 38% of Earth's gravitational pull. It's a gentle tug, really, one that would make you feel remarkably light on your feet. A person weighing 150 pounds on Earth would feel as though they weighed only 57 pounds on Mercury. You could jump nearly 3 times higher, and a dropped object would fall with a leisurely grace that might seem almost dreamlike. But Mercury's gravitational story is more complex than its surface gravity alone. This world's proximity to the Sun means it experiences some of the most extreme tidal forces in our solar system. The Sun's massive gravitational influence has locked Mercury into a peculiar dance, a 3-to-2 spin-orbit resonance that means Mercury completes exactly 3 rotations for every 2 orbits around the Sun. This gravitational choreography creates a world where the Sun appears to perform a strange backward dance across the sky, where some regions experience double sunrises and sunsets. Moving outward, we encounter Venus, Earth's mysterious twin cloaked in clouds of sulfuric acid. Venus presents us with a gravitational environment remarkably similar to our own. At 91% of Earth's gravity, Venus would feel almost like home beneath your feet. That same 150-pound person would weigh about 137 pounds on Venus, a difference so subtle it might go unnoticed. But Venus teaches us that gravity alone doesn't determine a world's character. Despite their similar gravitational pulls, Venus and Earth have evolved into dramatically different worlds, one a paradise for life, the other a hellish greenhouse where lead would melt on the surface. Then we arrive at Mars, the red planet that has captured human imagination for centuries. Mars offers us a gentler gravitational embrace, with surface gravity about 38% that of Earth. Like Mercury, Mars would make you feel surprisingly light, able to leap and bound across its rusty landscapes with an ease that would make Olympic athletes envious. But Mars's lower gravity tells a story of loss and transformation. Its weaker gravitational pull couldn't hold onto a thick atmosphere like Earth's. And over billions of years, the solar wind has slowly stripped away much of the air that once might have supported flowing rivers and perhaps even life. The asteroid belt between Mars and Jupiter presents us with gravity at its most delicate. Here, on worldlets like Ceres or Vesta, gravity becomes almost poetic in its gentleness. On Ceres, the largest object in the asteroid belt, you would experience only about 3% of Earth's gravity, A gentle push could send you floating gracefully through space for minutes at a time. These small worlds remind us that gravity isn't always about powerful attraction. Sometimes it's about the subtlest of influences, the gentlest of embraces that barely holds worlds together. But then we encounter Jupiter, the giant of our solar system, and gravity reveals its true power. Jupiter's immense mass creates a gravitational field 2.36 times stronger than Earth's. That same 150-pound person would suddenly weigh 354 pounds on Jupiter if Jupiter had a solid surface to stand on. The crushing weight would make every movement a struggle, every breath an effort. Jupiter's gravity is so powerful it shapes the entire architecture of our solar system, shepherding asteroids, capturing comets, and creating the complex orbital resonances that keep the system stable. Jupiter's gravitational influence extends far beyond its cloud tops. Its 4 largest moons, discovered by Galileo himself, demonstrate gravity's ability to create order from chaos. Io, Europa, Ganymede, and Callisto dance in perfect mathematical harmony, their orbits locked in resonances that have persisted for billions of years. Europa's subsurface ocean, heated by Jupiter's tidal forces, might harbor life in the darkness beneath its icy shell. Io's volcanic activity is powered entirely by Jupiter's gravitational kneading, making it the most volcanically active body in the solar system. Saturn, the jeweled crown of our solar system, presents us with one of gravity's most surprising characteristics. Despite being the second largest planet, Saturn's gravity is only about 107% of Earth's. This is because Saturn is less dense than water. If you could find an ocean large enough, Saturn would float. Yet Saturn's gravity has created perhaps the most beautiful gravitational sculpture in our solar system, its magnificent ring system. These rings are gravity made visible, countless ice particles dancing in perfect orbital harmony, sculpted by the gravitational influences of Saturn's many moons into the elegant structure we observe today. The outer giants, Uranus and Neptune, each present their own gravitational mysteries. Uranus, tilted on its side like a rolling ball, has a gravitational field about 89% of Earth's. Its unusual orientation, possibly the result of an ancient collision, creates the most extreme seasons in the solar system, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Neptune, the windiest world in our solar system, has gravity about 114% of Earth's. Its deep blue color and dynamic atmosphere are powered by internal heat sources we still don't fully understand, demonstrating that gravity's influence extends even to the mysterious processes occurring deep within planetary cores. Each of these worlds carries, within its gravitational field, the story of its formation, its evolution, and its future. The strength of a planet's gravity depends on its mass and radius, but the implications of that gravitational field extend far beyond simple numbers. Gravity determines whether a world can hold onto an atmosphere, whether it can support liquid water on its surface, whether its interior remains geologically active, and whether it can provide the stable conditions necessary for life to emerge and flourish. These gravitational signatures also reveal the dynamic history of our solar system. The current arrangement of planets isn't how they began their cosmic dance. In the early solar system, the giant planets migrated inward and outward, their gravitational influences reshaping the entire system. Jupiter may have wandered as close to the Sun as Mars is today, before being pulled back outward by Saturn's gravitational influence. This grand migration scattered asteroids, delivered water to the inner planets, and created the orbital relationships we observe today. The gravitational story of our solar system is still being written. The Moon is slowly spiraling away from Earth, its gravitational influence gradually weakening as tidal forces transfer energy between our world and its satellite. In about 5 billion years, the Sun will exhaust its nuclear fuel and expand into a red giant, fundamentally altering the gravitational landscape of the inner solar system. The outer planets will continue their stately dance long after the Sun has faded to a white dwarf, their gravitational relationships preserving the memory of our solar system's golden age. As we contemplate these gravitational fingerprints, we're reminded that we're part of this cosmic story. Earth's gravity, at exactly 9.8 meters per second squared, provides the perfect stage for life's grand performance. It's strong enough to hold onto our atmosphere and oceans, yet gentle enough to allow the delicate chemistry of life to unfold. It shapes our bodies, influences our evolution, and provides the stable foundation upon which all earthly drama plays out. Tonight, as you rest in Earth's gravitational embrace, remember that you're experiencing just one note in a vast symphony of gravitational forces. Each world in our solar system adds its own unique voice to this cosmic composition, creating a harmony that has persisted for billions of years and will continue long after we're gone. The gravity that holds you gently to your bed is the same force that shapes the rings of Saturn, powers the volcanoes of Io, and maintains the delicate orbital dance that keeps our solar system stable. In this gravitational symphony, every world has its part to play, every force has its purpose, and every mass contributes to the grand choreography that connects all things across the solar system. We are not merely observers of this cosmic ballet. We are participants, dancers, in a performance that began with the formation of our solar system and will continue until the last planet completes its final orbit around our aging star. The gravitational fingerprints of our cosmic neighborhood remind us that we are all connected, all part of the same elegant dance that gravity has been choreographing since the beginning of time. As we reach the culmination of our cosmic journey through gravitational forces, we find ourselves at a profound realization that extends far beyond the simple measurements of planetary pull. The G-forces we've explored throughout our solar system tell a story that encompasses not just the mechanical physics of attraction, but the very essence of how worlds are born, shaped, and sustained across the vast expanse of space and time. Each planet we've visited carries within its gravitational signature the memory of its formation, the echo of cosmic collisions that shaped its mass, and the ongoing dance of forces that continues to sculpt its destiny. When we speak of experiencing twice Earth's gravity on a world like Kepler 438b, we're not merely discussing the sensation of increased weight, but connecting ourselves to a universe where every gram of matter participates in an intricate ballet of celestial mechanics that has been choreographed over billions of years. The gentle pull of Mars at 38% of Earth's gravity whispers stories of ancient oceans and atmospheric loss, while Jupiter's crushing 2.5 times Earth's pull speaks to the gravitational shepherding that has protected inner worlds from cosmic debris for eons. These forces represent more than numbers on a scale. They embody the fundamental architecture of planetary systems, the invisible threads that weave together the cosmic web of matter and energy that surrounds us. Consider how the Moon's modest 16% Earth gravity created the perfect laboratory for human exploration, allowing our species to take those first tentative steps beyond our home world. Every footprint left in lunar regolith was made possible by gravitational forces that emerged from the collision of two worlds 4.5 billion years ago, when a Mars-sized object struck the early Earth and flung molten rock into orbit. The debris from that cataclysmic encounter eventually coalesced into our familiar companion, whose gentle pull now guides our tides and stabilizes our planet's axial tilt. The extreme environments we've encountered, from Mercury's scorching surface where you'd weigh nearly as much as on Earth, to the frigid realms of Pluto where gravity barely whispers at 6% of terrestrial strength, represent the extraordinary diversity of conditions that emerge when matter organizes itself under the influence of gravitational collapse. Each world's unique gravitational signature reflects its position in the cosmic hierarchy, from the failed star that is Jupiter, massive enough to shepherd asteroids and comets, but not quite substantial enough to ignite fusion, to the ice-covered moons of the outer solar system, where subsurface oceans might harbor life beneath shells of frozen water. The gravitational forces that shape our daily experience on Earth emerge from this same cosmic heritage. Every breath we take, every step we make, occurs within the embrace of a gravitational field that connects us intimately to the birth of our solar system in a swirling disk of gas and dust surrounding a young star. The calcium in our bones, forged in the nuclear furnaces of ancient supernovae, responds to Earth's pull just as it once responded to the gravitational fields of stellar cores, where temperatures reached hundreds of millions of degrees. When we contemplate the crushing gravity of gas giants like Jupiter and Saturn, we're witnessing the ongoing process of planetary evolution, where massive worlds continue to contract under their own weight, generating internal heat that drives weather systems and creates the conditions for dynamic atmospheric phenomena. The Great Red Spot of Jupiter, that enormous storm larger than Earth itself, exists because gravitational forces create the pressure gradients and rotational dynamics that sustain atmospheric circulation patterns for centuries. The ice giants, Uranus and Neptune, with their modest gravitational pulls relative to their size, represent worlds where the delicate balance between gravitational compression and internal heat creates unique chemical environments. Their tilted magnetic fields and unusual atmospheric compositions speak to formation processes that occurred in the outer reaches of our solar system, where temperatures were so low that water, methane, and ammonia could condense into solid building blocks for planetary construction. Even the smallest worlds in our solar system contribute to this gravitational symphony. The asteroid belt between Mars and Jupiter, prevented from forming a planet by Jupiter's gravitational influence, creates a dynamic region where countless small bodies follow complex orbital patterns determined by gravitational resonances. These rocky fragments, some barely large enough to walk across, others hundreds of kilometers in diameter, represent the raw materials from which terrestrial worlds are built. The dwarf planets scattered throughout the outer solar system, from Ceres in the asteroid belt to distant Eris beyond Pluto's orbit, demonstrate how gravitational forces operate across the full spectrum of planetary masses. Each of these worlds has cleared some of its orbital neighborhood through gravitational influence, yet none has achieved the dominance necessary to be classified as a full planet. Their modest gravitational fields create environments where ice can persist for billions of years, preserving chemical records of the early solar system. As we've journeyed through these diverse gravitational landscapes, we've discovered that the G-forces experienced on different worlds reflect not just their current physical properties, but their entire evolutionary history. The dense metallic core of Mercury, revealed through its relatively high surface gravity, tells us about the violent processes that stripped away much of its rocky mantle during the solar system's chaotic early period. The low density of Saturn, which would actually float if placed in a cosmic ocean, speaks to the rapid accumulation of gas that occurred when this world formed in the outer regions of the solar nebula. The gravitational forces that govern our solar system extend their influence far beyond the orbit of Neptune, reaching into the Kuiper Belt and Oort cloud, where countless icy bodies follow long elliptical paths around our Sun. These distant realms, where gravity's influence becomes almost imperceptible, represent the edge of our solar system's gravitational domain, the boundary where our Sun's pull gives way to the collective gravitational field of nearby stars. The study of gravitational forces throughout our solar system has revealed fundamental truths about the nature of planetary formation and evolution. We've learned that worlds with similar masses can have vastly different gravitational signatures depending on their internal structure and composition. We've discovered that gravitational interactions between planets can drive orbital migration, atmospheric evolution, and even the development of complex moon systems. The gravitational forces that shape our cosmic neighborhood operate according to principles that extend throughout the universe. The same inverse square law that governs the attraction between Earth and Moon also describes the gravitational relationships between stars in binary systems, between galaxies in clusters, and between the largest structures in the cosmic web. Every planet we've explored participates in this universal gravitational symphony, contributing its own unique voice to the cosmic chorus that has been playing since the first matter began to coalesce in the early universe. As we conclude our exploration of gravitational forces throughout the solar system, we're left with a profound appreciation for the intricate relationships that connect every world, every moon, every asteroid and comet in our cosmic neighborhood. The G-forces we experience on different planets represent more than mere physical sensations. They embody the fundamental organizing principles that transform chaos into order, that build complexity from simplicity, and that create the conditions necessary for matter to organize itself into the magnificent structures we observe throughout the universe. The gravitational dance that governs our solar system continues even now, as planets follow their ancient orbits, as moons raise tides on distant worlds, and as the solar system itself journeys through the galaxy, carrying all of its constituent worlds along for the ride. Every G-force measurement we've discussed represents a snapshot of this ongoing cosmic evolution, a moment in the 4.5 billion year story of our solar system's development. As we reach the end of our gravitational journey through the solar system, it becomes clear that the forces we've explored are far more than mere numbers on a scale. Each planet's unique gravitational signature tells a story that spans billions of years, from the violent collisions that formed these worlds to the subtle dance of celestial mechanics that continues to shape them today. The diversity of gravitational experiences across our solar system reveals the incredible variety of conditions that exist within just one stellar neighborhood. From Mercury's gentle tug that would make every step feel like a moonwalk, to Jupiter's crushing embrace that would flatten human visitors, each world offers a different perspective on how mass and space interact. These variations aren't just curiosities for future space travelers to consider, they're fundamental aspects of what makes each planet unique and habitable or inhospitable to life as we know it. Venus and Mars present particularly fascinating case studies in how gravity intersects with planetary evolution. Venus, with its Earth-like gravitational pull, demonstrates that similar mass doesn't guarantee similar outcomes. Its dense atmosphere and hellish surface conditions show us that gravity alone cannot determine a world's fate. Meanwhile, Mars, with its lighter gravitational field, has struggled to maintain its atmosphere over geological time, leaving us with a cold, thin-aired world that once might have harbored oceans and potentially life itself. The gas giants Jupiter and Saturn showcase gravity's role as a cosmic architect. Their immense gravitational fields don't just hold vast collections of moons in orbit, they actively shape the entire solar system's structure. Jupiter's gravitational influence protects the inner planets from many potentially catastrophic asteroid and comet impacts, while simultaneously sculpting the asteroid belt and governing the orbital periods of countless smaller bodies. Saturn's gravity, though less intense than Jupiter's, still creates spectacular effects, from the intricate patterns of its ring system to the complex orbital relationships among its numerous moons. The ice giants Uranus and Neptune remind us that gravity operates on scales both grand and subtle. Their gravitational fields, while strong enough to capture and retain substantial atmospheres of hydrogen and helium, also demonstrate the delicate balance required to maintain planetary systems at the edge of our solar system. The fact that these distant worlds can maintain such complex atmospheric dynamics and magnetic fields speaks to the persistent influence of gravitational forces even in the cold depths of space. Perhaps most intriguingly, the smaller bodies of our solar system, from Pluto to the various moons and asteroids, show us that gravity's influence extends far beyond the major planets. These worlds, with their weak gravitational fields, offer glimpses into different possible futures and pasts. They preserve ancient materials and conditions that have been erased from larger worlds, serving as time capsules that help us understand the solar system's formation and evolution. The practical implications of these gravitational variations extend far beyond academic interest. As humanity ventures further into space, understanding these forces becomes crucial for mission planning, spacecraft design, and the eventual colonization of other worlds. The low gravity of Mars might make it easier to launch spacecraft from its surface, but it also presents challenges for human health and equipment operation. The intense gravity of Jupiter's moons creates opportunities for gravitational assist maneuvers while simultaneously presenting engineering challenges for landing and surface operations. Looking toward the future, our understanding of gravitational forces across the solar system will prove invaluable as we search for life beyond Earth. The relationship between gravity, atmosphere retention, and geological activity helps us identify which worlds might harbor subsurface oceans, active chemistry, or other conditions conducive to life. Europa's gravitational relationship with Jupiter creates the tidal heating that likely maintains its subsurface ocean, while Titan's low gravity allows for the complex hydrocarbon cycle that creates its Earth-like weather patterns. The story of gravity in our solar system also connects us to the broader cosmos. The same fundamental force that determines whether you would weigh more or less on Mars also governs the formation of galaxies, the collapse of stars, and the expansion of the universe itself. By understanding how gravity shapes our local cosmic neighborhood, we gain insights into physical processes that operate on scales ranging from subatomic to cosmic. As we continue to explore and study our solar system, each new discovery adds another piece to the gravitational puzzle. Future missions will undoubtedly reveal new subtleties in how these forces operate, from the internal structure of planets to the complex interactions between magnetic fields and gravitational effects. The gravitational forces we've explored today continue to evolve, albeit slowly, as the solar system ages and changes. The next time you feel your weight pressing down on Earth's surface, remember that you're experiencing just one variation of a force that manifests differently across every world in our solar system. Each planet offers its own gravitational fingerprint, a unique signature that embodies billions of years of cosmic evolution and continues to shape the ongoing story of our celestial neighborhood. And now, as we return gently to Earth, remember this: even though your feet are firmly planted on one planet, your mind and your understanding can travel anywhere. Gravity may hold us down, but knowledge lifts us up. Thank you for drifting through the cosmos with me tonight. I hope you have a wonderful and an amazing night. Until next time, stay curious, keep wondering. This is Boring Science signing off. Cheers.